Ever wish you could just, like, whip out perfectly measured angles?
Yeah.
Using, like, the simplest tools.
Yeah, like just a ruler and compass.
Exactly.
Yeah.
That's kind of what we're getting into today, this whole world of geometric constructions. We've got some excerpts from this math textbook chapter all about building geometric figures.
And we really mean building them from the ground up.
Totally. Using just a compass and a straight edge.
It's about relying on, like, the core principles of geometry, not just, eyeballing it.
Right. It's kind of like those building games where you only have, like, a few basic pieces, but then you can make all these complex structures, right?
Absolutely.
Our mission, if we choose to accept it, is to unlock the secrets of these constructions. Like, why do they work? What's the logic?
And honestly, it's surprisingly elegant. You'll be amazed how much you can do with just those two simple tools. It's kind of mind-blowing, actually.
Well, it's not just drawing. It's more like...
It's proving theorems
Yeah.
with every arc, every line. It's all connected to these deeper geometric truths.
I love that. Okay, so let's grab our metaphorical compasses and straight edges. Where do we even begin?
Basics, always the basics. Let's start with the building blocks, and I think the angle bisector is a great place to start.
Okay, the angle bisector.
So picture this. You've got an angle, any angle at all, and your goal is to slice it perfectly in half.
Oh, yeah. I remember trying to do that freehand back in school. Never really worked out too well for me.
Yeah, it's tough to be precise, right?
Definitely.
But with a compass and a straight edge, it's like foolproof. The textbook walks us through the steps. You draw an arc from the vertex of the angle, right?
Yeah.
Then two more arcs from where that first arc hits the angle's rays.
Gotcha.
Finally, you connect the new intersection point back to that original vertex. Boom, you've got your angle bisector.
Okay, so that makes sense. But the really cool part is that it's not just a neat trick, right? It's actually proving something.
Exactly. It's a proof in action.
So how does this guarantee that we've actually split that angle in half perfectly?
It all comes back to triangle congruence. Triangles with the same size and shape, meaning they're identical.
Yeah.
Think about those two triangles the bisector makes. They share a side, the bisector itself, and we've basically made sure the other two sides are equal using the compass and those arcs we drew.
So we've got side congruence, right?
Exactly, SSS,
Yeah.
which matters because...
Because if the triangles are congruent, then all their corresponding parts have to be equal too, including those angles made by that bisector.
Ah, I see. So it's like we're creating a mirror image.
Precisely. It's a perfect reflection. We're not just drawing a line down the middle. We're literally demonstrating a core geometric principle.
That's so cool. I never thought about it like that before. Okay, so we've got the angle bisector down. What's our next construction challenge?
Let's tackle another essential construction, the perpendicular bisector. This time we're starting with a line segment, and we want to draw a line that cuts it perfectly in half at a 90-degree angle. Okay, I can already see how this would be useful when we start building, more complex figures. But first, how do we even construct a perpendicular bisector?
Right. So we'll use our compass again. You draw arcs from each endpoint of that line segment, and you want your compass set to be a bit wider than half the segment's length.
Okay, wider than half.
Yep. Those arcs are going to intersect above and below the segment.
Right.
Connect those 2 points where the arcs intersect, and ta-da, you've got your perpendicular bisector.
Nice. I'm starting to see the pattern here. It's like we're using the compass to, create these points that have very specific relationships to our starting shapes.
You're getting it. It's all about those relationships.
So how does this construction guarantee a perpendicular into bisector? What's the proof hiding in there?
Triangle congruence strikes again, but this time it's side angle side, or SAS.
That's it. Okay.
We've created 2 triangles that share that bisector line as a side, and they have 2 congruent sides that we made with those compass arcs.
Right. So because those triangles are congruent,
Their corresponding angles must also be equal.
and since we've divided that straight line, those angles on either side have to add up to 180, making them perfect right angles.
Exactly.
Wow, that's seriously clever.
Right. It shows you how a few, seemingly simple steps can unlock these really powerful relationships.
Okay, so we've got our angle bisector, our perpendicular bisector. What else do we need in our construction toolbox?
Well, no toolkit would be complete without the 60-degree angle.
Oh, true. It's everywhere. Equilateral triangles, hexagons.
Crucial angle, and of course there's a construction for that too.
Let me guess, it's elegant. Right.
Totally. So you start with an arc, like we've been doing, but then you use that same compass setting and you basically pace off another arc from a point on that first arc.
A saw.
Yeah, you keep the compass at that same width.
Ah, okay.
Connect the points where your arcs intersect, and boom, you've got yourself a 60-degree angle.
That's it.
That's it.
Wow. I'm starting to see how interconnected these constructions are. It's like we're not just drawing random lines. We're uncovering these like fundamental truths about geometry.
Exactly. And this construction, it inherently makes an equilateral triangle in the process. All sides equal, all angles 60 degrees. It's like built in.
That's incredible. Okay, so we have our angle bisector, our perpendicular bisector, our trusty 60-degree angle.
Yeah.
It feels like we're ready to build something a little more complex.
I think so too.
Hmm.
Are you ready to tackle some triangles?
Let's do it. I am ready for the challenge. All right, so are we ready to build some triangles?
Let's do it.
This is where it gets really interesting, I think. We've got our toolkit, right?
We're basic.
But now we have to actually use those tools.
Yeah, put into work.
It feels a lot more daunting now.
It's definitely more complex, for sure. But that's part of the fun, right?
Okay, yeah.
Remember we were talking about those constructions being kind of like puzzles? Well, now we've got to actually use those puzzle pieces
Yeah.
to achieve a very specific goal,
Okay.
which is constructing a triangle that meets these very specific conditions.
Right. And our source material, it jumps right into this scenario, and it feels very much like a brain teaser. Okay, so imagine someone gives you the length of the base of a triangle.
Right.
They give you one base angle,
Okay.
and then they tell you the sum of the lengths of the other two sides.
Okay.
Not the lengths themselves,
Right.
but the sum of the two together. That's not very intuitive.
It's definitely not as straightforward.
So how do we even, where do we even begin with that?
Yeah. So you can't just measure out those sides directly,
Right.
but we can use our tools, our compass and straight edge to kind of we can find those sides.
Okay.
So first things first, draw your base. You know that.
Yeah,
Draw the given base angle. Now here's where the construction gets interesting. Along that ray of the base angle, you're going to measure out a segment that's equal to the sum of those two unknown sides.
Okay, so we're making a big triangle.
Yeah, you're essentially building a bigger triangle that kind of hides the actual triangle we're trying to make.
Okay, so we're building the frame first.
Exactly. Now focus on that point where you marked off that sum, right?
Right.
That vertex of that bigger triangle. We're going to construct an angle bisector from that point down to the base of that larger triangle.
Oh, yeah. And that point where it intersects
Becomes the third vertex
of our original triangle.
Yeah.
That's wild.
Yeah.
It feels like magic. But it's not magic.
It's not magic at all. It all goes back to those congruent triangles again.
Right. So by making that angle bisector.
You've now divided that larger triangle into two smaller congruent triangles.
Okay.
And remember, the angle bisector, by definition, created two equal angles, right? And we've already got two sides equal because of how we set it up. So what do we have? Angle side angle, ASA congruence.
Okay.
Meaning all those corresponding parts of those two smaller triangles are identical.
Okay. So that means that the angle bisector also just divided that sum segment
Exactly.
into the two missing sides of our original triangle.
Precisely.
That's so cool.
It's pretty slick.
I'm starting to see why people get so fascinated by this.
Yeah.
It's really cool, but I have a feeling it's about to get trickier.
It does get a little trickier.
Because our notes mention constructions where you're given the difference of the sides, not the sum.
Right. So instead of the total combined length, we're given
the gap.
the gap between them. Yeah.
Okay, so how do we approach that?
So it's still about leveraging those same principles.
No.
Let's say we've got our base, our angle, and we're told one of those missing sides is, longer than the other by this certain amount.
Okay.
What's our first move?
Let me think. We had to draw the base and the angle again, right?
Exactly. Start with what you know. Draw the base, draw the given angle. But this time, on the ray of that angle,
Yeah.
you're going to mark off a segment that's equal to the difference between the sides.
Okay, so not the total lengths, but the
extra bit.
the extra, yeah.
Yeah.
Okay.
Now, think back to one of our tools,
Which one?
our perpendicular bisector.
Okay.
Instead of connecting that marked point, to the other end of the base, we're actually going to use it to construct the perpendicular bisector of that segment, that difference segment.
Oh, I see where you're going with this.
You're right.
Okay, so it's going to intersect that ray.
Yes.
And that's going to be the third point of our triangle.
Precisely.
Because we've essentially folded that difference, so
Yeah.
one side's longer and one's shorter.
That's a great way to think about
It's
it.
all coming together.
It's leveraging those properties, right?
Yeah,
That perpendicular bisector doesn't just cut it in half.
right.
It makes those right angles.
Yes.
So we're constructing it from the endpoint of our difference segment.
Right.
We're making sure that those two resulting segments along that angled ray are going to be different by that exact amount.
This is incredible. It's really cool to see how we can just like use these, use our knowledge to manipulate and like create.
It's very strategic, isn't it?
Yeah. But but this deep dive, it's not over yet, is it?
Not quite.
There's one more.
We've got one more challenge.
Okay.
Get ready, because this one's a bit of a mind blower.
Okay. That last one, I'm going to need a minute
It's a big one.
to wrap my head around this. So we're going to make a whole triangle,
Yeah.
and all we know is the total length of its sides and two of its angles.
It does seem impossible at first.
It seems like we have nothing to go on.
Right, but that's the thing about these constructions. They almost feel like magic, even though it's all based on logic, pure math.
So where do you even begin? It's not like I can just like draw the perimeter and like magically bend it into a triangle, can I?
You're actually surprisingly on the right track. The textbook says we start by drawing a line segment that's equal in length to the given perimeter. So think of that line as like all the material of your triangle just laid out flat.
Okay, so we're starting with the whole thing and then like figuring out how to fold it up.
Exactly. Next step, you're going to construct those two given base angles at either end of that line segment. Like we're, temporarily pretending this line is just one long unfolded triangle.
Okay.
Done.
And here come the angle bisectors.
You got it. You're going to bisect each of those base angles, then mark the point where those two bisectors intersect. That point, that's going to be one of the vertices of our final triangle.
Wait a second, hold on. We're not finding the sides first. We're finding the corner of the triangle first.
We're pinpointing that vertex. It's all about using those bisectors to divide that perimeter segment in just the right way. And now for the final elegant step from that intersection point, you're going to construct perpendicular bisectors down to that original perimeter segment. The points where those perpendicular bisectors hit that line, those are your other two vertices.
No, wait, let me see if I understand this. We used the angle bisectors,
Yeah.
and because they met at a point,
Right.
we made sure our angles add up to 180. But then, by carefully doing all that, those
Yeah.
perpendicular bisectors,
Yep.
we somehow divided that original segment into the three sides of our triangle.
You got it. Pretty cool, right?
That is amazing.
Yeah.
I would never have thought to do that.
It really shows the power of these constructions. We started with what seemed like very little information,
Yeah.
but using these tools, we've constructed this precise triangle. It's a beautiful example of how, seemingly simple techniques can solve what seemed like an unsolvable geometric puzzle.
This whole deep dive, it's just been awesome. We started with just these basic constructions, and then we learned about like the elegant geometry that makes them work. Then we use those to tackle these really complex triangle constructions.
Yeah.
And it all comes from just a compass and straight edge.
It's amazing, right? And these techniques, they've been around for centuries. Mathematicians, architects, artists, anyone who needed to create precise shapes, they've used these exact methods.
It's incredible.
Yeah.
And speaking of incredible, we like to end our deep dives with, a little something for our listeners to think about, like a final thought to kind of spark that curiosity. What do you have for us today?
So we've talked a lot about all the amazing triangles we can construct, right? But what about the limitations? So here's a question. If you only knew the three angles of a triangle, could you always construct it using just a compass and straight edge?
Ooh, that's a good one. It makes you think about all these relationships between the angles, the sides,
Exactly.
the rules.
The fundamental rules.
And on that note, we'll leave you to ponder that geometric mystery